Okay, so part 2, we're going to do orthogonal diagonalization. And you see, so the first part was more of an introduction and background. Here's where we're going to do the real work, and this is the video where you want to perhaps watch twice to understand what's going on. The other ones, that's just, we're going to take the things that we need from it, but that's it. Okay, so orthogonal diagonalization. So let's review first the fact of diagonalization, right? So if we have that if A is a matrix, then we call this matrix diagonalizable. Diagonalizable. If you can find the matrix P, so that P inverse A, P is a D, where this is a diagonal matrix. So this is a diagonal matrix, and this is an invertible matrix. We almost be talking about square matrices, right? So that was the definition. We saw that it can or cannot happen. Okay, so what we want to do now is try to get a better form for this. Namely, last time we talked about orthogonal matrices. Now, the matrix that we want to be orthogonal is actually this guy, this P here, because then this would just be P transpose. Okay, so we will say, I'm not going to write it down, but I will say that the matrix is orthogonally diagonalizable if you can find a P that is orthogonal. Okay, now we're not going to do the general case, and I'm going to stick to 2 by 2 matrices. So I'm going to start working on an example, and then we can go a little bit back more on reflecting on the general theory. So here's an example. A 2 by 2 matrix, 1, 2, 2, negative 2. Notice something about this matrix. It's a symmetric matrix. So that's the trick here. So all what we're going to do today is, this is about symmetric matrices. I will show that if you have a symmetric matrix, we will see that if you have a symmetric matrix, you can always diagonalize, and even better, you can always orthogonally diagonalize. So if for a symmetric matrix, we're going to be able to find an orthogonal matrix such that this is a diagonal matrix, and this is an orthogonal matrix. Okay, and remember, I don't need to write inverse here, I can write transpose, because the matrix is orthogonal. And of course this is much easier, because if P is orthogonal, then it's much easier. Remember, one of the things we had to do in diagonalization was actually calculate the inverse of P. Well, now we just take the transpose and we're done. Okay, so that's why the example that I chose is a symmetric matrix. Okay, but before we do, let's try to diagonalize it, just without orthogonal, just diagonalize. Okay, so step 1 was the eigenspace, the eigenvector values, the characteristic equation, and that was 1 minus lambda, 2 minus lambda, and then we have to put equal to 0, so this is 1 minus lambda times minus 2 minus lambda minus 4. Be very careful with all the negative signs, and that was, people in the quizzes got really stuck here, because if you cannot get the right characteristic equation, yeah, you're stuck, right? I'm sorry for that, but I'll try to give you matrices where it's not too hard, and in particular here, as I said, today we only going to work with 2 by 2, so that's at least takes away that hurdle. Okay, so but you still have to be very careful, right? So we have to expand here, so I'm falling out, minus 2 minus lambda plus 2 lambda plus lambda square minus 4. Take the like terms together, lambda square plus lambda minus 6. Correct? All right, be very careful here, and a good test is always, can I factor this nicely? And it's not always guaranteed, but okay. So we need two numbers that multiply to negative 6 and add up to 2. Add up to 1. So the bigger one should be a positive number, so I'm thinking a plus 3 and lambda minus 2 here. So this tells me lambda is -3 and this is lambda is 2. Okay, so step 2, let's do the eigenspaces. The eigenspace for lambda is 2. Let's do that first. So we take 2 from the diagonal, we get -1, 2, 2, -2, -2, that's -4. Right, subtracting from the diagonal, okay. And I need a pivot in the first place. I have a -1, so I'm gonna get rid of this by putting this here. I'm gonna write it. It's so little to do that I better write it. And then I do row operation 2, replace row 2 by -2 times row 1. Okay, with this pivot here, and I get 1, -2, and then so I multiply this -2 and adopt, I get 0, 0. Okay, so that's the 0 row I'm expecting. I need to add. I see I have a pivot variable x1, I have a free variable x2. Also in the quiz sum, if you don't have a free variable, something is wrong. Okay, and if you have too many free variables, something is wrong. Because in this case, we know how many free variables it can be. We have 2 different eigenvalues. There's only, and it's 2 here, 2 by 2. So each can have only one dimension, one basis vector, and therefore we can only have one free variable in each of the 2 cases. Okay? Good. So that's the first one. Oh, no, whoa, I have to write it down what it is, because I still don't know what it is. And this is also something, be careful, how does it work? Free variables are always equal to themselves. So start with that, because sometimes people seem to forget that, or put a 0 there or something. And then the blue variables, the pivot variables, can be expressed in terms of the green variables. So let's keep the colors a little bit. So how do we do this? Well, we have this equation. It says that x1 minus 2 times x2 is 0. So in other words, x1 is 2 times x2. So this in green now, that is 2 times x2. And then you factor out x2, and there should only be x2 here, nothing else. If there's something else than the free variable, you were actually forgot to do something or you did it wrong. Okay, so I get 2, 1, and then this is our basis vector. Okay, for this eigenvalue. So now for lambda equals, what's another one? -3, right? Yeah. So eigenspace for lambda is -3. Now we have to subtract 3 from, subtract 3 from, -3 from down means actually adding 3. So that is, where's my matrix? I'm going to put it here in front of me, otherwise I'm going to get, yeah. So I'm adding 3 to the diagonal because I'm subtracting -3. So that is 4, 2, 2, what am I saying? Adding 3, so 1. Okay. Yeah, you see here sometimes we don't have a 1, but for the first 2 elements, the first row is all even numbers, so there's no combination that ever is going to get 1. So I'm just going to divide by 4. Row 1, 1/4, row 1. It's not a big deal here, right? So let's see what we get. 1, 1/2, 2, 1, and then we do the row operation, row 2, row 2 minus 2 times row 1. So this is 1/2. Minus 2 adding up, that's 0, minus 2, oh, that's also 0. Of course, we need to have a 0 row. So again, we have our pivot variable x1, and we have a free variable x2. As I said, x2 is equal to itself, and what about x1? Well, from this equation we see that it is -1/2 x2. Remember, it has to be brought to the other side. So we get x2 -1/2, 1. Okay, so that's our second basis vector. And now we know what we do. We put these guys into a matrix P, and then we have the matrix P. Now, before we do this, let's get a better basic vector, right? We don't want a 2 here. Remember, we have said this, we can take x2 equal 2 here, and therefore we can take as basis twice this one, -1, 2. Much nicer, right? So, okay. So step 3, that's where we're at now. Step 3. We know what P is. P consists of these 2 guys in the order that I've did them. I mean, I just like to keep the same order. Okay. And what else? What is the diagonal matrix? Well, it has to be the corresponding eigenvalues, right? I did first 2 and then -3, so that's what I get. Great. Now, is this an orthogonal matrix? And the answer is no. And why is it not an orthogonal matrix? So remind you, orthogonal matrix. So this is the end of the story, except that we normally also have to find the inverse of P, but I'm going to not do that. Okay. So is P orthogonal? Let's start with that. Is P orthogonal? I'm going to say ortho. Okay. No. And why not? Well, remember, an orthogonal matrix has two properties: that the columns are unit vectors. In other words, they have norm 1. Another way of saying that is if you multiply them, the column with itself, you get 1. And different columns are orthogonal. Which means that if you multiply different columns, you get 0. Now, let's see what happens here. So we have the two columns here. Let's call them u and v, the two vectors. What is the norm of u? Well, that's the square root of the square of the first number plus the square of the second number. That's square root of 5. Okay, what's the norm of v? Let's do this now too. This is the reason I'm doing this, because I'll need it at some point. Remember, it's squaring the first number, that's 1, squaring the second number, and adding is 4, so again, square root of 5. Okay, so this is not verified, so that's why I say no, because it should have been 1 to get this condition. What about this condition? Well, if you verify, you see that u times v, the dot product, is 0, right? Just check it out. 2 times minus 1 plus 1 times 2. That's 0. But we knew this. From the previous video, I said that if you take eigenvectors with different eigenvalues, then they are orthogonal. No brainer. Don't have to think about it, don't have to calculate. We know that is the case. So just by putting these eigenvectors, they come from different eigenvectors, I'm already guaranteed that the different columns are orthogonal. The only thing I don't have is that they are actually unit vectors. But there was a trick to make from a regular vector a unit vector. And the trick was very simple. Divide by its norm. So if you can make that into, to make a unit vector from it, you just take u, divide by its norm. So in this case, the norm was radical 5. So what I'm saying is, what am I saying? Okay, let's look at this. So, sorry, let me. No, sorry. Where are my u and v? Here's my u, right? So let's go with this u. So I'm saying, so this u, what is this? Well, that is the vector. I'm going to write it a little bit weird, like 2, 1. It's this vector divided by the square root of 5, which means really that we have to divide each entry by square root of 5, right? So this vector is now a unit vector. Let's verify it, right? What's the norm of this vector? You take the square of the first element, that is 4 plus square root 5 squared, that's 5. So 4/5 plus 1/5, 5/5, 1. Okay? And the same is true for v, right? You just take v and divide it by its norm. And we get the vector, I'm going to do it right away because the norm is the vector minus 1 over radical 5 and 2 over radical 5. Now, we don't bother about rationalizing, we just leave it like that. So, conclusion, if I now put p, these vectors, and can I do this? Yes, because remember, what does this mean here? I took this basis vector for the eigenspace for lambda is 2, right? Because that was a very nice one, simple one. But I can take any value of x2. So the value of x2 that I'm taking now is actually 1 over radical 5. 1 over the norm of this basis vector. And then I get also another basis vector. We know that we can take anything that we want here. Any multiple. We did it here to just get rid of the denominator, but in fact, some sense we took the wrong multiple. We should have taken this multiple, or rather 1 over that number thing. So in other words, this is still an is still a basis for an eigenvector, so I can always put this here in my matrix P. Okay, my original matrix P was this one. So I'm going to redefine my matrix P. I'll make it now the better P. I'll make it a green P. So the green P is going to be the matrix where I not take the original basis, but this normalized. So unit, so we make a unit vector out of this, and this process is called normalization. We make the norm 1. Okay, so this is the first vector, and the second one we do this 2, minus 1 radical 5, 2 radical 5. And now I claim that this is an orthogonal matrix. Why? Well, we know already that since the columns are different eigenvectors, or rather eigenvectors corresponding to different eigenvalues, we know that they're orthogonal. So this is automatic. It's a 2 by 2, so it's simple. But notice that this is even true for longer, bigger sizes as well. What about the first thing? The columns have to be unit vectors. Well, we made them unit vectors, so we're done. So this is an orthogonal matrix. If you don't believe me, take its transpose and multiply this matrix with its transpose, and you'll see you get the desired identity matrix. Okay? So cool, no? So in other words, if you start with a symmetric matrix, then you do this process, a 2 by 2 matrix, symmetric 2 by 2 matrix. I have to be careful because when you go to higher sizes, it's still true, but it is a bit more complicated. I'll say something about that later, but for now I'm going to do another example, okay, and just work it out in detail again. So what you do is you do the usual thing, and at the very end, instead of building P by using your basis, you take the basis, but you then normalize these bases and then put them in the matrix. Okay, I'll do it on an example. Let's see. Let me take something here from the. Okay, let's do this one. I hope that I'm just picking a matrix here. If it doesn't work, then I'll change it. Let's do 1, 2, 2, 4. Okay, it's a symmetric matrix, so this is of course important, right? Otherwise, it won't work. Okay, so step 1, we need the characteristic equation. 1 minus lambda, 2, 2, 4 minus lambda, that's equal to 0. So we get 1 minus lambda times 4 minus lambda minus 4. That is 4 minus lambda minus 4 lambda plus lambda square minus 4. The 4's cancel, so I get lambda square minus 5 lambda. That is lambda times lambda minus 5. Great. So I find lambda is 0 is one eigenvector, and lambda is value, and lambda is 5 is the other one. Okay, step 2. We calculate the eigenspaces. So nothing has changed, right? Eigenspace for lambda is 0. That means we take 0 from the diagonal. Means it's the original matrix. 1, 2, 2, 4. We have the 1 there. Very nice. So we do row 2 minus 2 times row 1. I get 1, 2, 0, 0. Okay, we have our pivots. This is the pivot variable, and the green guy is the free variable. So we can write x1, x2 in terms of the green variable only. The first tells me it's minus 2 times x2, and as I said, x2 is always equal to itself. So x2, we get minus 2, 1. So now we're going to do an extra step here. Extra step. We're going to calculate the norm of this matrix. So what is the norm of this matrix? That is just, well, remember, it's the square root of the sum of the squares. So minus 2 squared, that's 4. 1 is, it's again radical 5. I'm sorry, I didn't mean to get the same answer here, but it happens. Okay. And so now we're going to take this x2 1 over this thing. Be careful, we have to divide by it, right? In the normalization, we divide by the norm. We calculate the norm and then divide by it. So our basis vector that we're going to use is going to be minus 1 times 1 over radical 5. Okay, you can write it this way. That's the first one. And so if we put this one in, this is a unit vector, and this is going to be the first column in my matrix P, or the second, or however I want to order them. Okay, so eigenspace for lambda equals 5, so I have to subtract 5 from the diagonal, get minus 4, 2, 2, minus 1. Okay, I'm gonna have to divide here row 1 by minus 1/4 row 1, and then I get 1 minus 2, right? Yes, and then 2 negative 1, so and then do the next operation. Row 2 minus 2 times row 1, and I'm gonna get a 0 in the bottom, right? No, what did I do wrong? I'm dividing by negative 4, that's not minus 2, that's minus a half here, that's why I got... See, I knew I was wrong because I was not going to get a 0 row there. That's how you can always double check that you didn't make mistakes, and you see a silly mistake here, dividing by 4, and I get... Okay, so now it's true, right? If I multiply this with 2 and add up there, I get, no, this one is just copied, I get 0, and I get plus twice a half minus 1, that is indeed 0. Okay, so x1 is our pivot variable, x2 is our free variable, and so we get x1, x2. The free variable is always equal to itself, and what is x1? Well, it is a half x2. So I factor out x2 and get a half 1. Now, you see fractions are almost inevitable, so I'm not going to bother by the fact that I have a fraction here. I'm just going to do the extra step. Extra step is find the norm of this vector. What's the norm of a half 1? Well, it's the square root of the square of the first one. 1/2 squared, that's 1/4 plus 1. So we are dealing here with 5/4, right? So this is square root of 5/4, which if you want is square root of 5 divided by 2. Okay, so now the basis I'm going to take is the vector that I have there, a half 1, divided by this guy, which means multiply it with its reciprocal. Okay, and now you see actually, I still get rid of the 2 for some nice reason if I multiply this out, but I still have the radical 5, so I'm just going to leave it like that. Okay, so now we are done. Step 3. P consists now of these 2 normalized bases. So it's perhaps nicer now to write them really as fractions. So I'm gonna, right, so I'm copying this guy here, the basis on top, and now the other one is, okay, let's multiply it out. 2 times a half over 5, so this, okay, so this is actually 1 over radical 5, and this is 2 over radical 5, right? So I guess 1 over radical 5, and this is 2 over radical 5. And so this is an orthogonal matrix, guaranteed, unless I made a mistake. And what is the corresponding diagonal matrix? Well, I did what first? 0 first, I think, yeah, and then 5. All right, and that's how we do orthogonal diagonalization. Now, we can combine this with what we did in the previous time about power of a matrix. So I'm going to now add this extra. It was not the original question, and sometimes I won't ask it, but I might ask it. So what would be a to the third? Let's calculate a to the third. Now, what's a 2 by 2? You can do this, right, of course. But I want to do the fancy way, and the fancy way would be, remember, what was the deal? In the general theory, we had this, and then we brought the piece to the other side in the right way, so that we would get this thing. I hope you still remember this, otherwise go watch the video. And then we used that a cube is the same as p d cube p inverse, and we just had to calculate this to get a cube. Now d cube was easy, so this would have been what? P times d cube. That's taking the cube of a diagonal matrix is just taking the cube of the diagonal elements, that is 0, 0, 0, 1, 25. And then P inverse. But P inverse is P transpose, because it's an orthogonal matrix. So what I have to can write, so sorry, I can write my, let me write out my P here too. So my P here was minus 2 radical 5, 1 radical 5, 1 radical 5, oops, and 2 radical 5. Okay, this happens to be a symmetric matrix, but okay. So even more, it's a symmetric matrix. So if I take the transpose, it's the same itself. But okay, that might or not be. So let's just, I'm just writing down the transpose now. This is the first column. This is the second column, but it's the same matrix, obviously. Okay, and now I have to multiply it out. Now, granted, these radical 5s are a little bit of a nuisance. But we could have taken them out, right? So remember, these are scalars, and this is, so out of here we can take a 1 over radical 5 out, and here 2. So we can 1 over radical 5, another 1 over radical 5, and then we have left minus 2, 1, 1, 2, 0, 0, 0, 1, 25, and then minus 2, 1, 1, 2. That simplifies our calculation. It's not necessary, but it makes it easier. So then we see this is 1 over 5, what am I saying, 125. Radical 5 times radical 5 is 1 over 5, right? And let's work out, okay, I'll work it out, these two guys here. The first thing is, if I multiply with the first row, of course, I can get zeros and zeros, and the second one is going to be 125 and 250. Okay, and now multiply this out. The first element is 0 plus 125. The second element is 0 plus 1, 250. Then we have 0 plus 2 times, so 250. And then we get 0 times 2 times 250, that's 500. By the way, is it symmetric? Is that coincidence? No. That we knew. That if you multiply two symmetric matrices, it's going to be symmetric again. So again, if this would not be symmetric, something was wrong, because our original A was symmetric. So this is a fast way also of finding a multiple of these matrices, and it's still, I mean, it's only power 3, but it would get a little bit more annoying. If 1/5, I forgot my 1/5. Whoa. So I have to actually divide everything by 5, right? So there's 25, and this would be 50, 50, 100. Almost made a mistake. Okay. So that's the deal, and as I said, we're going to only do 2 by 2 matrices, which is very straightforward in this way. It always works, and you just have to normalize and as an extra step, and then you're done. Okay, what about matrices of higher, bigger size? Now, what's the problem is, this works without any problem if you work with matrices that are have different eigenvalues. If all the eigenvalues are different, then this works without any problem. And I could perhaps even do an example of that. I'm not going to do it today, but perhaps in the next video or so, to show you that it works. However, if the eigenvalues, if you have a double eigenvalue, then you know that you have to have 2 eigenvectors, basis vectors. And there is when you take 2 basis eigenvectors of the same eigenvalue, you don't know that they're orthogonal. They might not be. Remember, the trick that we had was for those that had different eigenvalues. But if they're the same, but the good news is actually you can always make them orthogonal. But that is something that is not in the syllabus, that used to be in the syllabus, but they have taken it out, and this is called Gram-Schmidt. If you want to read it in the book, it explains it actually in 7.2, but I'm not going to cover this in this course. All right? Okay, so I do some more reviews on it later and homework problems, so we can, and then eventually we're going to do a quiz on this too.